So now you are ready for the next step of the aldol reaction. This is called the aldol condensation. This step happens after aldol addition, and it's a dehydration reaction that happens with the aldol. So what I'm going to do is take this aldol, this kind of generic aldol that I drew up here. I'm going to redraw it down here without the yellow circles around it. Like this. R prime, R, and R prime. And this also uses hydroxide. The aldol condensation can also be done with acid, H3O+, but it's pretty much never done with acid because the aldol addition is done with a base, and so you already have the base present for the condensation, so there really isn't any reason to switch to an acid. And this reaction requires some heat. This reaction usually happens automatically. Like when you do aldol addition, it pretty much always just immediately does condensation. So in order for us to be able to do aldol condensation, one of the R and R prime groups that we have written here specifically needs to be a hydrogen. So I'm going to take away R prime and I'm going to make it a hydrogen. We have to have a hydrogen, another hydrogen on this molecule for it to work. And the product of the condensation reaction looks like this. This is, like I said, it's a dehydration where we're getting rid of water molecule and we're forming this double bond between the alpha carbon and the beta carbon. So this molecule is sometimes nicknamed an alpha beta unsaturated aldehyde or ketone or just carbonyl. And that name is coming from the fact that we have created a site of unsaturation in between the alpha and the beta position for that carbonyl compound. So again, I'm going to put a little note on here that this reaction is usually automatic after the aldol addition. One time that it wouldn't be automatic would be if you didn't actually have this extra alpha hydrogen. If it's not there, then this reaction can't take place. So this reaction is probably less magical than the addition reaction. When you're looking at it, it's probably not that difficult for you to see how this reaction occurs, but we're going to draw the mechanism anyways. I'm going to draw, I want to use this guy right here, this one. So I'm going to recreate the product of the aldol addition. I'm not going to draw the hydrogens that I drew up there on carbon number 6, but I will put the numbers on just so that you can see the consistency between the two molecules. There we go. So in order for this reaction to work, we really have to focus on the carbon that has the OH group. We have to focus on this carbon right here. And we also have to focus on the carbon to the side, I want to say to its left. It's not always going to be to its left. We have to focus on the carbon with the OH group and the carbon that is in between the carbonyl and the OH group. That's where the double bond goes. So these are the two carbons that we're attempting to work on right here. In order for this reaction to be successful, one of those carbons has to have the OH group, which it will, and the other carbon has to have a hydrogen, which it may not. It doesn't always have it, so you're going to have to look out for it. The hydroxide ion, remember this is done with OH, the hydroxide ion comes in and it grabs that alpha hydrogen. The carbon hydrogen electrons are going to come up. Technically, we should draw it first as becoming a lone pair on, what is that, carbon number 2. So that's what I'm going to do. Like that's the purest way to draw this mechanism. lone pair right there, like that. And then that lone pair is going to come back in to make the carbon-carbon double bond and get rid of OH as a leaving group. And you know OH is not a great leaving group, and that's one of the reasons this reaction needs heat to kind of help it go along. But also this reaction is driven by the formation of a more stable product. We're forming an alkene and it's conjugated with the carbonyl group. So it's an extra stable molecule that we get out the end of it. And that's one of the reasons why this works, why the reaction works. You will also see if depending on the structure of your aldol, there's potential for cis trans or EZ. This is where I'm going to lose carbons, 1, 2, 3, 1, 2, 3. So you do have the potential for cis trans EZ, and in terms of deciding which is major, which is minor, we're just still going to use the same rules that we always use, paying attention to steric hindrance. But it's really not going to come up that much of asking you to draw major and minor. So let's go back to the worksheet and see if we can do condensation on the addition reactions that we already drew. So here's where we are here. And this says, if possible, continue to the reaction by drawing the mechanism and products for a condensation. So if it's possible, let's do condensation on these guys. So first we have to decide if it's possible. And the way that we do that is find the carbon with the OH group, and then find the carbon that's in between the carbonyl and the OH group. So if we're going to do it, this is where we're going to put the double bond. We're making a conjugated molecule, or we're not doing this at all. We're either going to conjugate the double bond or nothing's going to happen, because we're not going to get anything out of putting a double bond out here. An isolated double bond, no way. So in order for this reaction to work, our carbon number 6 needs to have a hydrogen on it, and it does. So that means that we can do this. We're going to use another hydroxide, and I'm going to be a little bit lazier in the mechanism than I was just previously. So we're going to grab that hydrogen, and I'm just going to go straight for everything happening all at once. Carbon hydrogen electrons are going to make that double bond, and the OH group is gone. And let's see what we have. That's carbon number 5. There's carbon number 6. It's got an isopropyl group on it. That's the bond to carbon number 1, 2, 3, 4. Let me number those carbons and make sure I didn't leave any out. 5 to 6. 7, 8 is down there on the isopropyl group. There's 1, 2, 3, and 4. And so it looks like I just automatically drew the major product, probably. But I'm not worried about cis versus trans or E versus Z. I'm really mostly concerned about you getting all of your carbons connected in the right way. Let's take a look at this next one and see if we can do condensation down here. So in order to do condensation, the first thing that we have to do is find our alpha carbon, find our beta carbon, find the carbon that has the OH group, find the carbon in between the alcohol and the carbonyl group. And in order for this reaction to work, we have to have an OH group on one of them, and we have to have an alpha hydrogen on the other. Does that guy have an alpha hydrogen, carbon number 4? I don't know why I'm asking you, because you cannot talk back to me. There is no alpha hydrogen here. And because there's no alpha hydrogen there, this guy can't do condensation. You have to have an alpha hydrogen on that spot for the condensation to work. There is nothing to eliminate. So that means that this right here is the end of the reaction. It's not going to go any further than that.